Hi, in this video we are going to talk about the implementation of the maximum flow problem, and we are talking about the implementation of the minimum cut also. So let's get started. In this tutorial I'm not going to start it from scratch because it would take a lot of time, and I highly recommend you write it out several times and to be able to get a grasp of it and to understand as much as you can, because to be honest this is the most important algorithm as far as graph algorithms are concerned. Several problems out there in practice relies heavily on this maximum flow and minimal cut theorem, so I think it definitely worth understanding and implementing this algorithm. So let's get started. We need a vertex class with an ID, with its name, and with a boolean visited. We have seen it several times earlier. It's quite simple, I think. The class edge is a bit trickier. Of course, we have a reference to a vertex, start vertex. I'm going to rename it because we name it start vertex, not from vertex. Okay, we are going to have a target vertex as well, and as I said earlier in the theoretical part, we will have two properties, the capacity and the flow. And it's very important that the flow must be less than the capacity, and the flow has to be greater than 0, of course. We're going to have a constructor as earlier, and getters and setters. It's very important that there are three methods that worth mentioning. In the first get other vertex, it's quite straightforward. We will need to get the other vertex, so it's going to get a vertex, and if it's equal to the start vertex, then return the target vertex, else return the start vertex. So if it gets this, it is going to return the other one, and if it gets this, it's going to return the start vertex. I think it's quite straightforward. So let's move on. The get residual capacity too, it's going to get a vertex, and we have to decide whether it's a backward edge or a forward edge. As I said earlier in a theoretical basis, if the vertex is the start vertex, then return the flow, because it means it's a backward edge. Else, we know that it's a forward edge, so we have to return the capacity minus flow. It's very important. And to add residual flow to the vertex, we have to specify what vertex we want to add this little flow. I call it delta flow. After finding the augmenting path and computing the bottleneck capacity, we have to add this little flow, and we have to determine whether it's a backward edge or a forward edge. So if it's a backward edge, I said earlier that we have to subtract it from the given flow, and if it's a forward edge, we have to add it to the flow. So it's very important. These two methods are very important. It's the basis of the Ford-Fulkerson algorithm and the advanced GARP implementation. So we are going to have a graph class. It's going to store the adjacencies. So here we are not going to store the adjacencies in the vertex, for example. We create the graph. I think it's a good programming practice, but it's up to you. For example, in breadth-first search and depth-first search, in the easier algorithms, I like to have composition, which means that for example, breadth-first search, if you remember, the vertex has a reference to a list of vertices called adjacency list. So I like this kind of programming, but it may be a bit nicer anyways. So it's going to have the number of vertices, number of edges as integers, and it's this is maybe in this class Ctrl-Shift-F to format. This is the most important method. We just add an edge and we get the adjacency list with the ID and add the edge, and get the other one and add the edge in order to construct the residual graph. So that's all. It's not that hard. If you are going to write it out several times, it will be straightforward, I think. And for Fulkerson, we are going to have, I try to make as many comments as possible. So we have an array of booleans has passed in residual graph. It is true if S to V pass in residual graph. If this is a path in the residual graph, the last edge on shortest residual path is equal to the last edge on shortest residual S to V path. It's very, very important. Of course, we have a value of the maximum flow. We have a reference to the graph. We have a reference to the S. I don't like these kinds of words because it's very, very hard. For example, if it would be a legacy code to decide what does it mean S and T, but because I use these symbols in the theoretical video, I use the same here. But I usually like the S vertex, for example, or try to specify what it is. But anyways, just for demonstration purposes, it will be okay. So, okay, the constructor, we get a graph, a source vertex, and a sink, or target vertex, whatever. And we run the Edmonds-Karp algorithm. And as I said earlier, we run this algorithm while we have an augmenting path. So we have a bottleneck with positive infinity. We compute the bottleneck capacity and we add it to the residual flow, and then increment the bottleneck capacity. It's not that hard to. We have this isInCut helper class, helper method, in order to detect whether the given vertex is in the minimal cut or not. We will see it in the app class. Get value to return the maximum flow itself. And this has augmenting paths, as I said earlier. Edmonds-Karp algorithm relies heavily on breadth first search. So if you are familiar with breadth first search and depth first search, you see that we have a queue, we have a while loop and isEmpty. So it's a typical implementation of the breadth first search. We're just searching for a new augmenting path. Yeah, and if we detect it, then we return the has path in residual graph. Okay. And in order to test it, I made this. It is the problem we are talking about in the theoretical video. We just have to do this. It's not that nice. We just have to do it in order to detect the minimum cut. We add edges to the graph. It took about 10 minutes to write it out, so I think it's the best way not to build it from scratch. It would take a lot of time. Okay, so it's a Ford Fulkerson algorithm. We run the Edmonds-Karp algorithm and we print out the maximum flow, and we print out those vertices that are in the minimum cut. So we loop through the vertex list, and if this vertex is in the minimum cut, then we just get it and print it out to the console. And if we see, or we run this maximum flow. Okay, we see that the capacity, the maximum flow is 28, as we saw earlier, and the vertices in the minimum cut is S, vertex 3, vertex 5, and vertex 6. And we came to the conclusion that the minimum cut is equal to the maximum flow. So that's all about implementing the Edmonds-Karp algorithm and maximum flow problem. Thanks for joining me and watching my videos. I hope you enjoyed it. Thanks again.